So welcome back. In the last video, we looked at the first of the two contributions to pressure losses in piping systems, and that was minor losses. In this video, we're going to turn our attention to pipe friction, and this is the friction that occurs in long, straight runs of pipe. So this equation, which we've seen before, but I haven't described in any detail, is called the Darcy-Weisbach equation. And the very first thing we see there in parentheses is our rho v squared over 2 term, so the kinetic pressure term. So realize this velocity in this is the average velocity in the pipe. Because if we go inside of the pipe and measure the velocity in detail, it's going to be higher at the center line, then it's going to fall off near the walls, but for most flows it's actually quite uniform. So this velocity here is the average, or so-called bulk velocity in the pipe. So rho v squared over 2 is the kinetic pressure. So realize that term, rho v squared over 2, has units of pressure. So if we were working in SI, that would be pascals. In front of that kinetic pressure term, we need to multiply by the L over D ratio of this pipe, or the length to diameter ratio. So L is just simply the length of the pipe, and D is its diameter. Now notice that's a dimensionless ratio. So length and diameter have to be expressed in the same units here. Doesn't matter what it is. They could both be meters, both be centimeters, both be furlongs, doesn't matter. As long as they're the same, this ratio will be correct. So that's the L over D ratio. So we start to see there, and this makes a fair bit of sense, a long pipe has a large pressure loss due to friction. And so that certainly makes sense, but it turns out that small pipes also have large frictional pressure losses. So the L over D, or length to diameter ratio. The very last part of the Darcy-Weisbach equation is a friction factor, and this is called the Darcy friction factor. And that is sort of similar to the minor loss coefficient in that it's a multiplier applied to the kinetic pressure to get the pressure losses. But this one we don't look up in a catalog for different types of pipes. Calculating this F is a little bit more complicated than just looking up a minor loss coefficient, because this F is a function of a couple of things. Okay, so the friction factor that we use is a function of two things, really. The first one is pipe roughness. So if the inside of the pipe is very, very rough, the friction factor will be larger. If the inside of the pipe is smooth, the friction factor will be lower. The other thing that the friction factor is a function of is something called the Reynolds number. So friction factor, a function of two things, pipe roughness and Reynolds number. Well, before we can really go any further in showing you how to calculate friction factor, we need to define what this Reynolds number is. And the Reynolds number is an extremely important number in a large variety of fluid mechanics applications, and pipe flow is no exception. It's probably one of the most important parameters when you're studying a pipe flow is to know what the Reynolds number is. So we're going to set this equation aside for a moment and talk about the Reynolds number, because we need to be able to calculate the Reynolds number before we can calculate the friction factor, and we want to understand, where did the Reynolds number come from? Well, to understand where the Reynolds number comes from, we're going to take a look at some experiments that were done quite some time ago by a fellow named Osborne Reynolds. So Osborne Reynolds did a whole series of experiments using flow visualization in pipe flow. So we're going to illustrate what that looked like here. So here we have a pipe, and the flow is from left to right. And in Osborne Reynolds' experiments, this was a transparent pipe. So he had water flowing from left to right in this pipe. And what he did was inject some dye on the center line of that pipe. And he observed this dye as it traveled downstream. Now you're actually going to get to repeat this experiment in one of the labs in this class. So when you do that lab, you'll see something very similar to what we're going to see here. Well, he observed, so what Osborne Reynolds did was he varied quite a few things. He certainly varied the flow rate through here. He varied the diameter of the pipe. with different viscosities and different densities, and he found that sometimes, under some conditions, what would happen is that stream of dye, or the filament of dye that came out of this injection port here, just traveled straight down the pipe right at the position that it was injected. So he could move this around, and it didn't matter where he put it. The dye just went straight downstream, similar to what I'm showing here. Well, that has since been named laminar flow. And it's called laminar flow because all of the particles of fluid are just traveling in straight lines right down parallel to the axis, or in laminar layers. So that's one type of flow that he observed. Now, as he changed all of these parameters that I mentioned, what he found was sometimes he would observe a very, very different behavior. Same injection of dye, but what would happen is very shortly after the dye was injected, it would be mixed very thoroughly through the entire cross-section of the pipe. And that is now named turbulent flow. So one of the fundamental things that we need to understand as we analyze pipe flows is the difference between laminar and turbulent flow. Because it turns out that the way we calculate that friction factor is different for laminar and turbulent flow. Eventually we'll see the equations that we use, but there's a different equation for laminar and turbulent flow. Now, before we worry about the equations to calculate friction factor, we need to continue this discussion and understand what Reynolds number is, because it's used to calculate that friction factor. Continuing with the discussion of this figure, let's go back to this laminar flow case. And I'm going to call the velocity in this direction u. So that's the u component of velocity. And we're going to go into this pipe to this position right here and measure the u component of velocity as a function of time. Okay, so just imagine that we're putting a velocity probe of some kind in there, and it measures that component of velocity, and we're going to do a time trace of that. We're going to measure it as a function of time. Well, if we were to do that, in laminar flow, what we would get is just a perfectly straight line. So there would be a steady value of u. It would not be fluctuating at all. Steady value of that velocity. Now, as we move that point to different spots, the velocity would change because it's highest near the center and lowest, in fact, goes to 0 at the wall. But the point here is that it doesn't change with time. It's very, very steady. Now, if we were to do exactly the same thing in the turbulent flow, so go to some spots in the flow, measure that u component of velocity with respect to time, what we would see is a fairly wildly fluctuating velocity trace. And this is the main characteristic of turbulent flow compared to laminar flow, is it's characterized by random fluctuations. Now, realize that if we were to look at the average of these, so the mean value of this velocity, maybe it's there somewhere, it's still a positive number because on average, certainly the fluid is still traveling from left to right here. We have a flow from left to right, but the instantaneous value of that velocity is fluctuating quite wildly around that mean. So this is a characteristic of turbulent flow, fluctuations. Now, I want to go back and look at the difference in the way this dye is behaving in these two cases, because it's tied directly to what's happening to the velocity. Now here, I've been talking about the component of the velocity along the axis of the pipe, the so-called u component. But if we were to look at the component of the velocity perpendicular to the pipe, so perhaps call that v, if we were to measure that component of velocity in the laminar flow, it would be 0. So if we were to plot it on here, it would just be a line right down at 0. However, if we were to do that for the turbulent flow, measure the component of velocity perpendicular to the axis of the pipe, it would also be fluctuating much like this, only it would be fluctuating down here around 0. It might look something like that. okay? Because there's no bulk transport up or down here. There's nowhere for the fluid to go. But at any instant in time, if you were to measure the velocity right there, it would probably have a component perpendicular to the axis of the pipe. And that component would be fluctuating wildly, just like the axial component. Now, the reason that that's important is that explains why he saw this very distinct difference in how quickly the dye is mixed across the whole cross-section of the pipe. Due to these fluctuating velocity components perpendicular to the pipe, the dye is carried out to the walls very, very quickly in a turbulent flow, and it really isn't in a laminar flow. Now, when you do this in the lab, you will notice that this distinct stream of dye does get smeared a little bit as you go downstream, but that's just diffusion. It's not fluctuations in the velocity of the water that's doing that. The dye is just diffusing out into the surrounding water slowly. This turbulent mixing is happening much, much quicker than that molecular diffusion could possibly happen. So this, again, is a phenomenon you'll see in the lab, but the important thing here is that the frictional losses in these two scenarios are quite different, and we need to calculate them in different ways. Now, on to the Reynolds number itself. Well, this is based on observations that Reynolds made. So to summarize some of the observations that he made, he found that turbulence could be achieved by, so if he had a laminar flow and he changed something to create a turbulent flow, he found one way he could do that was by increasing the velocity. So just increasing the flow rate through the pipe, the flow would go from laminar to turbulent. And in the lab, that's exactly what you're going to do. The only knob you have to turn is really the flow rate through the pipe. So as you increase the velocity, you will notice this transition from laminar to turbulent flow. Now, the other thing that he found out he could do was increase the pipe diameter. So keeping everything else constant, increasing the pipe diameter would trigger turbulent flow. Also, increasing the density of the fluid would trigger turbulent flow. So high velocities, large pipe diameters, and high density of the fluid tend to cause turbulent flow. The last property that he investigated was actually viscosity, and it had the opposite effect. So he could trigger turbulence by looking at lower viscosity fluids. So as the viscosity reduced, the transition to turbulence happened sooner. So if we take all four of these quantities and we put the first three in the numerator because they increase the likelihood of turbulence, and we put the fourth one in the denominator because it decreases the likelihood of turbulence, we get what is called the Reynolds number. So the Reynolds number is defined as rho v d over mu. So rho is the density of the fluid, v the average velocity of the fluid, d the pipe diameter, and mu the dynamic viscosity. So you'll notice that a high Reynolds number gives turbulent flow, and a low Reynolds number gives laminar flow. That's why we've arranged these things in the numerator and the denominator the way we have to be consistent with these observations. High Reynolds number, turbulent flow; low Reynolds number, laminar flow. Now, it also turns out that as long as you use a consistent system of units for all of these things, so in SI that would be kilograms per cubic meter, meters per second, meters, and for the dynamic viscosity, Pascal seconds. If you put all those units in there, you'll find out they cancel out. So Reynolds number is a dimensionless number. It doesn't have any units. So to calculate the friction factor for any pipe flow, calculating the Reynolds number is an essential first step to do that. Now, once you've got the Reynolds number, where does the friction factor come from? Well, this is where the difference between laminar and turbulent flow comes in. For laminar flow, the friction factor is 64 divided by the Reynolds number. Now notice, Reynolds number is a dimensionless number, and friction factor is also a dimensionless number. So there are no units attached to either of those quantities. For turbulent flow, we have a couple of options for calculating the friction factor. The first of those is called the Colebrook equation, and this is the most accurate of the two options that I'm going to present here. So as you can see, the Colebrook equation is quite a bit more complicated than the equation we need to use for laminar flow. For laminar flow, the friction factor is only a function of Reynolds number. But for turbulent flow, the friction factor is a function of two things: Reynolds number and the roughness of the pipe. So this term here, epsilon over d, is called the relative roughness. And again, it's the ratio of two things. Epsilon is the pipe roughness. So this is going to be a function of the condition of the inside of the pipe and the material it's made out of. If we have a smooth pipe, then epsilon is 0. D here is the diameter of the pipe. And so you need to make sure that the units of the roughness and the units of the diameter are the same, so that this relative roughness is a dimensionless number. The Reynolds number comes into the Colebrook equation right here, and it, of course, also is a dimensionless number. Now, as I said, the Colebrook equation gives quite accurate results. The problem with it is that it's an implicit equation. So friction factor, which you're typically calculating using this equation, is on the left-hand side. That's fine. But it's also on the right-hand side. So the only way to solve this is through iterative means, or your calculator, or whatever means you have for solving implicit equations. So it's a little bit more difficult to use, but it is very accurate. And like I said, this term is here to account for the effect of pipe roughness. Now, the second equation that I'm going to present for calculating friction factor for turbulent flow is called the Haaland equation. And if you look at it, you just glance at it, you say it's almost the same thing. But the critical difference with the Haaland equation is that the friction factor only appears on the left-hand side. There's no friction factor on the right-hand side. Well, this makes it quite a bit easier to use, because if you know your relative roughness and you know your Reynolds number, you substitute them in here, calculate friction factor, and you're done. Now, it's not quite as accurate as the Colebrook equation, but it's within about 2% over a very, very wide range of conditions. So if you're doing hand calculations, I'd recommend that you just use the Haaland equation, because that's much, much easier. But if you're doing a spreadsheet or a computer program where you can handle the iteration required in the Colebrook equation, then you would get more accurate results using the Colebrook equation. The next thing that I want to show is something called the Moody diagram. And the Moody diagram is just a graphical representation of everything that we see on this slide. So here's the equations that you would need if you were going to actually plot a Moody diagram. Now, the reason I'm showing a Moody diagram is because it's an alternate way to calculate these friction factors just by looking them up off of the Moody diagram. And certainly in the past, before we had calculators and computers, this is the way friction factors would be arrived at, is looking them up on the Moody diagram. Now, it's still worth learning what the Moody diagram looks like, but we don't typically use it anymore to actually come up with numbers for the friction factor. However, it's a really good synopsis of these equations and exactly how they behave and how friction factor changes as we change Reynolds number and roughness. So the first Moody diagram we're going to look at here is just a sketch that I've made, and then we'll look at a real or an accurately plotted Moody diagram after this. First thing to realize is a Moody diagram is a log-log plot. So the vertical axis is the log of the friction factor. The horizontal axis is the log of the Reynolds number. Now remember, friction factor is a function of two things: Reynolds number and roughness. So because of that, we're going to see a whole family of curves on here as we build up our picture of the Moody diagram. So the first thing we'll show on here is the equation F is equal to 64 divided by the Reynolds number. And when we do that on a log-log plot, we get a straight line with a slope like this. So when we have laminar flow, This is the relationship between Reynolds number and friction factor on the Moody diagram. Now you'll notice that I've plotted this down here at low Reynolds numbers, because remember, low Reynolds number flows are laminar flows. Now, what exactly do we mean by low Reynolds number? Well, for our purposes, we're going to define laminar flow as any flow where the Reynolds number is less than 2000. Likewise, over here, we're going to be defining turbulent flow as a flow with a Reynolds number greater than 4000. Well, you may be asking, what do I do if the Reynolds number is between 2 and 4000? Well, the problem with that is there's really no reliable way to predict whether you're going to have laminar or turbulent flow in that range of Reynolds number. So that's a transition region where it's really practically impossible to predict which you're going to get, because the transition from laminar to turbulent flow is a stability issue. A tiny little disturbance can trigger a flow to transition from laminar to turbulent. So there's a range of Reynolds number there where it's really, really difficult to predict. So the Moody diagram usually just shows that as a transition region. On the turbulent flow side of that, so for Reynolds numbers greater than 4000, remember both the Colebrook and the Haaland equation show that the friction factor is a function of Reynolds number, which we have as our horizontal axis, but it's also a function of roughness. So we need a whole family of curves on this two-dimensional plot to show how F varies with both Reynolds number and epsilon over d, the relative roughness. Well, the first line that we'll put on here is for smooth pipes. So if the relative roughness is 0 and we plot the Colebrook equation, we would get a line that looks like this. So a line with a negative slope like this, similar to the laminar flow line, but it's a curved line. And as we go to a higher and higher Reynolds number, the slope of this, it never flattens out, but the slope does get less and less. So that's the line for smooth pipes. Now, as we look at higher and higher values of roughness, we will see a whole family of curves on the Moody diagram for rough pipes. Now, again, these lines are sloped and a similar shape to smooth pipes, but the difference is these lines for rough pipes flatten out. So if the Reynolds number is high enough, they become horizontal lines. So there's a line here that divides this transition region here from this region where we have horizontal lines. So this is called complete turbulence, or fully rough zone. So each of these lines is for a particular value of relative roughness, and to the right of this boundary, they're essentially horizontal lines. But to the left of this boundary, they're sloped lines. So back here, the friction factor is a function of both the relative roughness, which means which of these lines are we on, and the Reynolds number, which means where are we left to right along that line. However, to the right of this line, when we're in this fully rough zone, the friction factor becomes only a function of the relative roughness. For instance, as we go from here to here, the friction factor doesn't change. So in that region, in fact, everywhere where this line is horizontal, the friction factor becomes independent of Reynolds number. Now, that's an important feature of the Moody diagram, and it's a feature that we're really going to take advantage of when we're solving problems later on. And I'll emphasize that quite a bit during a couple of the examples, that the friction factor becomes independent of Reynolds number if the Reynolds number is high enough. And by high enough, I mean to the right of this dotted line, or in this fully rough zone where these are horizontal lines. Now what we're going to look at is a real Moody diagram. By real, I mean a Moody diagram that's plotted accurately using the equations on the previous slide, so using the Colebrook equation essentially. So this is the Moody diagram out of your textbook. And so it's a lot more detailed than the little sketch we had on the previous slide. But we'll just take a look at some of the details. So you'll see the vertical axis here is friction factor. And if you look at this, you'll see that it's a log scale. Horizontal axis is Reynolds number. And again, if you look at the labels on the axis, you can see that that's a log scale. Here we have our laminar flow line, and the equation is actually given right on here. F is equal to 64 over the Reynolds number. Here is our smooth pipe line for turbulent flow, sort of the lower bound of this whole family of curves. And then as the pipe roughness increases from 0, which it is for a smooth pipe, these lines of constant roughness get higher and higher and higher. So you'll notice on the right side of the plot here, each of those blue lines is labeled with its particular value of relative roughness. So for instance, right here is a relative roughness of 0.01. So this line is a line of constant epsilon over d of 0.01. So if our relative roughness was 0.01, so meaning the roughness elements inside of the pipe are 1% of the pipe diameter, then this is the line that we would use. So if we were looking up friction factors graphically, we would figure out what our Reynolds number is, and we would figure out which one of these lines we were on. So if we had a Reynolds number of, let's say, 1 million and a relative roughness of 0.01, there's 0.01. Here is 1 million, 10 to the 6. So we go up this line until we hit our relevant line of constant epsilon over d. So the point we'd be operating at is right there. And we go from that point straight over. This would be our friction factor. So that's 0.38. Oh, sorry, 0.038. So the friction factor for a relative roughness of 0.01 and a Reynolds number of 1 million is 0.038. So that's the way we used to calculate or look up friction factors, but now we would just use the Colebrook or the Haaland equation instead. But it's still very useful to know where we are on this Moody diagram, because when you use the Moody diagram, you can tell at a glance, depending on what Reynolds number you're working with, whether you're in this fully rough region or not, whether you're back in this transition zone. So that's the Moody diagram. And again, it's really just a plot of the Colebrook equation. Now the last thing we want to look at in this video is what do we do if we have non-circular pipes? So everything we've talked about so far has assumed that the pipe is circular, and we have the pipe diameter in many of the equations that we've been talking about so far. But what do we do if we have non-circular ducts? So square or rectangular or triangular cross-section ducts. Well, in that case, we use the concept of a hydraulic diameter to calculate the Reynolds number. And the hydraulic diameter is defined as 4 times the cross-sectional area of the duct divided by the wetted perimeter. And wetted perimeter is just the length of all of the sides of the duct added up. Now, if you calculate the hydraulic diameter for a circular pipe, you'll find out that it's just the diameter of the pipe. But if you have a square duct or a rectangular duct or a triangular duct, you would use this equation to calculate a hydraulic diameter, and then you would use the hydraulic diameter to calculate the Reynolds number, and in the Darcy-Weisbach equation to calculate the frictional pressure drop. So this video has looked at how to calculate frictional and minor pressure losses in piping systems. In the next and last video in this module, we're going to take these piping systems and hook them up to pumps and see how the pump characteristics and the piping system characteristics work together to define how much flow we're going to get through a particular piping system when it's attached to a particular pump. So we'll see you in the next video.